We started 10:15, right? Yeah. He came in as a guest. Okay. How do I elevate him to a participant?
Hi, Ben. Amanda here. You should be able to be marked as a presenter now. Are you able to share your screen and unmute yourself and do a test? You're still muted, Ben. Hey guys, Amanda here. Is anyone else hearing really strange background noises? If so, indicate in the chat, please. It almost sounds like an what in the world is going on? Hey, Ben, I'm going to go ahead and ask you to get out and get right back in. And Sean Schuler, I'm going to ask you to do the same thing too. I have no idea what's going on, so we got a couple minutes. So let's hang up and start again. Okay, thanks, guys. Okay, Amanda again. Hey guys, are you able to, is it sounding better now? If so, indicate in the chat. Yes, okay, wonderful. We'll bring Ben back in now. Thank you very much. I have no idea what happened, but thank you for your patience. Okay, Ben, I see you there. Now, would you go ahead and give an audio test for me since we've been having such challenges?
Sure, never a dull moment with internet meetings.
That's right, that's right. Okay, thank you so very much. So we will get started in 1 minute. Thank you so much, and I apologize for the delay, and yeah, that's how it is.
It's fine, we're just going to blame Sean anyway, so.
We should blame Sean, of course.
Yeah.
Absolutely. All right, good morning, everyone. I hope you're really enjoying GIS Day. If you don't know me, I'm Amanda O'Daniel. I'm very proud to be the room moderator for this, I guess, virtual room moderator for Ben. Let me go ahead and tell you a little bit about Ben, and he can talk about what he's going to be presenting today. So Ben has been working for the city of Huntington. Actually, that is my hometown. I don't know if he knows that or not, but that's actually where I'm from. Huntington, Indiana, over on Byron Street, Ben. And he's been there for the last 4 years. He has a master's in GIS from Penn State, and he leads the IGEC Developer Support Group, and currently serves as the president of the Northwest Indiana Information Community, which is called NIGEC. So that's pretty amazing. And I know that there's some people from that organization on with us today. So this is an interesting thing. So this is Python multi-threading, and I'm really shocked that we have this many people in, but it's not as scary as it sounds. And he's going to talk about it, and he's actually really going to talk about how you can speed up your scripts by, he says, 1,000%. So Ben, let's go ahead and talk about what you're going to be doing. And remember, once again, you guys are muted, but go ahead and ask any questions. And if it's important about the presentation, I will go ahead and interrupt. Otherwise, we'll wait to the end. Thanks so much. Ben, it's all yours.
All right, sounds good. Everybody, it looks good. I told it to share the other side, but according to my little highlight, I think we're good. I am me, you are you. Let's go here. This isn't exactly the best kind of presentation for this type of format because I have no idea how much you're all enjoying it, but we'll see how it goes. So my journey into Python was a lot like my journey into fly fishing. Everyone kind of goes through basic steps. So step one, you're just happy to get that rope to cast and move. Similarly in Python, you're just happy to be able to click run and have something come out at the end without your computer blowing up. So then as you progress through your career and move on to stage two, you're looking to try and get as much distance as possible. You're looking to try and get your Python scripts to run as fast as possible and get some horsepower into those things. And then three, as you finally move and kind of start mastering all the basics, you get to trying to present things accurately and trying to do that with the least amount of effort. Or as in like Python, you're trying to get things to run efficiently with the least amount of code and the least amount of memory overhead. I am somewhere between 2 and 3, depending on the day. I'm somewhere between 2 and 3, depending on how it goes with Python, and depends how the week's going. So in this talk, we're going to be talking about how to get you to get some of your tools and kind of upgrade them to turn from something adding a little more horsepower to your scripts, get a little more in there. So give your best Tim Allen grunt in there. Our 911 director is actually named Tim Allen, and he looks a lot like him. So I give him a lot of stuff, and he's probably not happy with me, but it's a good time. So let's give a couple examples from the Python world. So one of the things that we do constantly is we do utility invert calculations. So we'll go out with the GPS, shoot new rim elevations for manholes and things like that. And then that information has to be taken over to the pipes information for the measure downs to get the invert elevations for the pipes. So you'd shoot a manhole, add the elevation to the manhole, add the elevation to the pipe, calculate by field. It was a very tedious process. So I scripted a way to convert the manhole, to take the manhole attributes, throw it to the pipes, and then do the math on the pipes. The one problem is that I did it from a GIS standpoint, and I used all the ArcPy tools and did a lot of select by locations. So there's only one issue with that. It worked, but select by location is extremely heavy. It takes a lot of computational resources. It's very slow. It took 2 minutes to update 187 pipes. So for our 30-some thousand pipe segments network, it was not very feasible to run that. So took to the internet. Like all good solutions, the answer's out there maybe. And as opposed to using ArcGIS, I looked to internal Python problems because a lot of problems aren't unique to our industry and they've actually been solved in the language in other places. So I came across the MapReduce framework. So MapReduce is a 0n complexity problem, which basically just means it scales extremely well. It doesn't get logarithmically difficult the more pieces you add. So basically all this states is that what you do is you'll iterate through and you'll build a dictionary, because dictionary lookups are extremely fast. You'll build a dictionary of your key value, and you'll have this common value between, like, say, an ID number and like a temperature value for a site, and you'll build those two dictionaries, and then you'll make all your lookups and joins across those two dictionaries. So it makes things extremely fast. So here's an example. This would be a dictionary look time it loop. So just getting this geohash, basically it's a nonsense number that's a unique identifier to a location, and it takes 131 nanoseconds tested over 1 million loops. So you can make 10,000 dictionary lookups in the exact time it takes to run one SQL-based query in Pandas. So for every one lookup you would make in a Pandas dictionary, I can run 10,000 against this. So now with this MapReduce style framework, I can run it against the entire pipes datasets in under 8 seconds. So this is the kind of stuff that we're going to be talking about today, and how you can implement some of these language-based things to make your lives substantially easier, and it's pretty cool in the process. So let's talk about the great trash cart debacle in 2018, namely who calls them trash carts. That's what Republic told me they had to be called. They're cans with wheels, but whatever. The city brought in trash. We had a contractor. We used to have our own trash services, and then we contracted it out with Republic Services. And we had to get a list of all the current residents in the city. So we took water utility data, we took our address data, took parcel data, and had to merge them all together. And anybody who's ever merged addresses from 3 different sources knows it is a colossal pain, because nothing matches. I think we had like an 80% one-to-one match, and even then it just was a nightmare. It took me 2 weeks to hand match all of them, and it was 2 weeks of my wasted life I'll never get back. So in comes GIS Day of like 2018, I think. And I went to a talk by Richard Ryan Stevens from the health department, who talked about geocoders. And I thought, boy, that's genius. I should just use the composite locator to geocode those addresses, and then I can just move them parcel wise, as opposed to having to do a one-to-one join or something like that, because we have very dirty data. So this is kind of a modified script that he gave me. We'll go through it here real quick. So it takes some variables, just collects inputs for input table, output location. You specify which column is in that table as a CSV and what the ID is. It uses pandas, the request module, and time just for time it. And then TQDM is a cute little progress bar. Very lightweight, very nice to use. So moving into it, the load data frame function takes your input table, address column, and the ID that you'd like to read to. It creates an empty list to hold the results from the geocoding, and you're going to use pandas.read CSV to read that into as a data frame. Check to make sure that the column is within that data frame. If it's not, just say, hey, what's up? You don't have a column. And then instead of using a print function, you have to use TQDM write, because it does TQDM kind of overrides the system output. So you can't use print. You have to just use that. It's the same thing. Not a big deal. And then looping through the pandas data frame, there's a lot of different ways to do it. They have some built-in iterators and things like that. But I found that just zipping them together was actually the fastest way to do it, even though not the cleanest. So what you're doing here is you're taking zip 2 data frames, and what zip does is it takes 2 lists and will glue them together as side by side. So then you can get the unique ID and address. So you're getting attribute 1 from the first list and 2 from the second list all at once. And like I said, it's not very Python-ish, but it was the fastest way to get them through. So then you're going to do some error handling. So you're going to run geocode for each address and each unique ID in those columns of your Panda data frame. If there's any exceptions, raise them, and then add those to this empty result list up here, which will just be a list of individual dictionaries for each result, and then return that result. So then moving on, this is the geocoder. This is what handles all the heavy lifting. So the geocoder URL points to the Indiana composite locator, which is outstanding. It has some gobbledygook here. That's part of the API call. And basically using .format, which is Pythonese, to say, hey, we're going to put the single line right here, and it's going to fill in our address in this point for this string. So then you're going to use the request module to get a request using that geocode URL that you're going to format from that address that came in. and it's going to make a call to the server. It's going to come back as a JSON, which we will parse into a dictionary. And then for the result dictionary, it's kind of broken up into a bunch of pieces. You're going to want the candidates. And this 0 says, give me the first highest matched result of those candidates. And then we're going to break apart location, attributes, and score from 3 different pieces. That's just a multi-line assignment. And then we're going to build an output dictionary. So this output dictionary says that unique ID is the ID number, address, the XY locations, just doing some things to bunch it all up nicely into a nice little dictionary and then return that output. So that's going to go back to that function we just looked at. So then moving on, once it's done, we'll start down here actually. So this is the if name main. If you're not familiar with it, it basically just says if you're running this module, not as a module, as a standalone program, do this. And it says, hey, run the main thread. So the main thread, again, takes those input table, address column, ID column. Time.time basically is for time measurement, so we can see how much faster we're getting. And then it's going to load that data frame. That was that first function we looked at. And then once it gets the results from that, it'll write output, which is simply just data frame pandas to CSV. You're just going to say, hey, take that data frame we made, save the whole thing as a CSV, and tell us that it's been created. And then and then measure the time and print the time. So let's go ahead and geocode those 6,000 some city address files and see what we get. This only takes about 45 minutes, so bear with me. Any minute now. So you're seeing we're getting about 10 iterations a second. Okay, so obviously we're not going to sit there and wait through the entire thing. We actually got faster internet between when I recorded this test and when I did it the first time, so it only took 10 minutes this time, but I think we can all agree that the Geocoder is a little slow. It works amazingly well. 45 minutes of my life was way better than the 2 weeks of my life and my coworker's life that we wasted the first time. But let's see if there's anything we can do to speed it up, okay? So in order to understand kind of why it's slow, we have to kind of go back and talk about Python as it exists in general and some of the limitations of the language. If you don't know, Python is actually named not for the snake, but for Monty Python and the Holy Grail. That's how it gets its name, and a lot of references to that are in the documentation. So Python has a global interpreter lock, okay? And what that basically means is that only one thread can run on one machine at one time, and it locks everything else down. There's a couple different ways to do it, but it makes it easy, simple. It doesn't use all the threads on your fancy multi-core machines, but it does make sequential things run really, really fast, which was all we had back in 1990s when Python was written. So it kind of sacrificed potential other things to make what it was basically good at work quicker. So there's 2 types of problems that can really, really be substantially made better with multi-threading, and that is I/O-bound problems and CPU-bound problems. So an I/O-bound problem would be something that your computer does a little bit of work, your CPU does a little bit of work, and then you're just waiting forever for some sort of input-output call. So like writing to a file disk, waiting for user input, or requesting an address from a server or something like that. So as an example, you have, when you buy your processor, you get these little numbers that say cache and L2 cache, and they're like 8 megs or 12 megs. And then you have your RAM and then your hard drive and then something over the network. So each cycle, you're allowed to kind of do something with each of those steps. So to think about it, to do some processing on your processor's internal cache, it would take 3 seconds. To do something at the L2 cache, the slightly extended, which is like 12 megabytes, you get 14 seconds. Now, to move something to RAM, which you probably have 30 gigs now, it's 250 seconds. But then to do something on the hard drive, it would take 1.3 years. So you could see how if you do some stuff on the computer, you can do really, really fast calculations of the CPU, but then just sending one thing out to the network is like an eternity of the computer waiting and doing nothing. Your processor is literally doing nothing for 7 years, waiting for that information to come back from the network. So let's kind of let's do an example, right? So let's say you're having a party, okay? You're gonna throw a rager, all your friends are invited, and you got tons of friends, and what you're gonna basically do in a sequential problem is you're gonna take one letter, you're gonna give it to the mail, you're gonna put it in the mailbox, and that mailman's going to pick it up and he's going to deliver it to your friends one at a time. So your friend gets it and he's so excited, just be out of his mind, and he's going to fill it out immediately and send it back to the mailman, who's then going to deliver it to you. You're going to check them off, and then you're going to start the whole process over and send the next letter. So it takes you not very long to write that letter and put it in the mailbox, but the whole time the rest of this process is going, mail's letter. The whole time you're doing this process, you're just kind of sitting here doing nothing, idly waiting. I couldn't decide on my favorite gift for this portion, so I put the runner-up in there as well. You married folks will get that. So that's the sequential problem. So then if we look at a CPU-bound problem, that is something where your CPU is just churning and burning, doing a bunch of math, and you're just at the limitations of how fast your computer's brain can run. So a good way to think of this is like mowing the lawn. No matter what you do, you can't really do anything. You just have to start at the beginning and go to the end. You can buy a bigger CPU, a bigger lawnmower, but there's nothing you can do intrinsically to make that lawnmower run a little faster. I guess you could overclock it, give it some more voltage, but it's hard on your knees. So let's go ahead and speed up that old geocoder. And let's first kind of define some terms. Concurrency is like threading or asynchronous, and it's kind of just talking about doing multiple things at once, whereas parallelism is a subset within concurrency, and that is actual multiprocessing. So that is physically doing two things at once, as opposed to doing multiple things as two things at once. So you can kind of think of it like cooking. So in sequential, if you wanted to make dinner, you would have to like preheat the oven, wait for the oven to get preheated, chop the carrots. Once you're done with that, move on to something else. Whereas concurrent, you could start the oven, go do something else while it's doing its thing, go put the rice in the microwave or whatever, go do something else. You let other things kind of do their thing while you're working on other stuff, as opposed to waiting for them to finish. And then parallelism would just be like sequential, but having two people in the kitchen at the same time. Okay. So let's look at the multi-threading solution. So multi-threading, you have one CPU core that's going to make multiple threads, okay? So you'll have one thread that'll do something, send out its request, and as it's waiting, it makes this blocking IO call. It will just stop and wait for that response to come back, and that allows another thread to do something else. So Python threads are really, really good at doing nothing. So each of these threads has a little bit of overhead, just kind of note that. But basically your computer will do something, and while it's waiting for a return, your computer can move on and do something else. So in the mail example, that would be like, instead of delivering one letter at a time, you would send out 30 letters at a time, limited by your computer or mailman carrying case. So if you have some people that are less excited to come to your party, you're not hung up waiting for them. If you'd send 10 letters out, the mailman would return the 2 fastest responses to you, and then you could give him 2 more immediately. So you're not waiting on all those slower pieces to send out your next invitation. So multi-processing or parallel processing is basically you would split your Python interpreter into 2 different pieces. So you actually have 2 physical Python instances running on your machine. So you do have some overhead for creating a second, third, fourth interpreter, but overall you're going to break that problem up a lot more. So kind of be aware of how much time you actually need to break apart. As far as our lawnmower explanation, it would be like cutting the grass, but you would get a second mower. So it would cut your grass cutting time in half because you have 2 mowers. But in reality, nobody only has 2 cores at this point. I mean, my computer has 12, so you get the gist. You can also solve I/O bound problems with parallelism by breaking multiple. So this is our I/O bound problem from earlier, where your CPU has a little bit of work and then you're just waiting for those file types, by breaking them across multiple threads or multiple cores. But you will have some speed up because you're having 3 people process. But it's not going to be as efficient as using threading because you still have this lag time. So using our mailbox example, it would be like delivering all the letters one at a time, like in the first examples, but so not as efficient as multi-threading, but it would be better than sequential. Pop quiz, everybody's favorite. So how can we make our geocoder faster? What type of problem is it? What's the answer? Go ahead and throw it in the chat if you wish. Any brave souls out there? That's right, threading. You're all geniuses. Great job, everyone. So how do we implement threading and concurrency in Python? So it used to be kind of hard, threading, multiprocessing, you had to create pools and things like that. But now with the concurrency package, it's really, really simple. It comes baked right in. So for concurrent, you have multithreading, which comes from concurrent.futures.threadPoolExecutor, and then you give it a number of workers. And then for multiprocessing, you have concurrent.futures.processPoolExecutor, and it gets its number of workers from your system data. It just pulls the number of cores off your machine. You could set it if you want to, but there's not really a reason to unless you want to lower it from the total amount of cores that you have. You have two functions within those. You have .map, which runs just like the map built-in function of Python, and also submit. So there's kind of two little differences. We'll talk about that in a second. So let's talk about multi-threading using the map first. So you're going to go ahead and from concurrent import futures, and we're going to specify a max number of workers as 20 because we don't remember there is a little bit of overhead for creating threads. So this will be your function that you would do something for a single file or response. And then for the concurrent, we would give it that list. And one thing you want to do with workers too is you always want to take the minimum of whatever your max worker number is and the length of the list you're processing, because you don't want to create 20 threads if you only have 9 things to process. So that's just a quick little line to check to make sure you're not creating more than you actually have. Okay, then we're going to go ahead and use the with syntax, which handles all the cleanup that we might need. So with futures.threadPoolExecutor, given that worker that we check to make sure right here that we don't have too many, as the executor. So then in here we're saying, okay, executor.map function and process list. So what that's going to do is it's going to take a list, and then for each of those items in that list, it's going to apply them as variables to that function. So that's what map does. You take a list of things and run a function on each one, and as this is the argument for that, and then we'll get a response back from that. Okay. If there's any questions, stop me. Whatever, I'm going to assume everyone's got it, and they're just waiting on bated breath. So for the multiprocessing for the map framework, same thing. From concurrent import futures, we're going to define our function that does something, and then we're going to create our concurrent processing with our list. And this time we don't need to do the workers thing because it just gets it from the number of cores. You could if you wanted to override it, but I just let it go. So with futures, and this time we're using process pool executor as opposed to thread pool, and we're going to do the same thing. Executor.map function for process list. So let's go back. So this is the threaded example for like I/O problems, and this is the processing for CPU bound problems. Okay. So what if you need to give more than one argument, because map only allows for one argument? You could use a partial, but that's a pain. So we're going to use submit if you want to get a little more technical, a little lower level. So map is real easy. It just sends in one thing. If you want a little more control, you can use the submit. So same thing up here, workers or concurrent futures, the max workers of 20. And then here's our function that will do something. Okay, so then we're getting into our process list. Workers, same line here. Now we have a little futures list. So what that's going to do is it's going to hold our, what they're called futures. So when you send something out to the thread pool to be executed, you get a future back, which is basically a placeholder saying that there's nothing here right now, but it will be something in the future. It's called a promise in other languages like JavaScript, but that's what we're going to hold just to check on. So same with syntax with the thread pool executor as workers as executor. Now this time map will iterate for you, but we have to do the iteration because we're not using map. So in that process list, for each item to process, we're going to run a for loop on it. And we're going to use executor submit to that function up here, the item to process. So now, because you're using submit, you could add 5 or 6 inputs or whatever you would need to per function. And that's going to give us our future back. And then for our future list, we're going to append this future to this list. So it's going to hang out here until it does nothing. And then a super cool thing to do is futures.asCompleted of this future list, add them to this done iterator. So basically, once these are done, it's a non-blocking call, but as these are completed, they can pop off into this other iterator and you can process them as they come back. So then for item in this iterator, you can process them as they come back while waiting for the others to complete. So super cool. And you can put that cute little progress bar around this with the done iterator. So let's, thought I had a multiprocessing version. Submit's the same way. It's just the same exact code. It's just without the workers. So let's go ahead and speed up that old geocoder. So here's our new, all the input main stuff's all the same, but let's take a look at our new geocode. So here's the same address format. We're going to do the same thing with the geocode URL and the results, but we're going to take out that processing of building the dictionary, and we're just going to return that response. So we get the result back from the geocode as well as the ID and the address, and we kick that out. So we can just keep making those fast calls over and over again. So then we also built a process results. So it will take the result dictionary, the address from this, and it will build that candidate's dictionary. So here's the logic from the other one. It takes that first candidate, builds it to the attributes, and then builds the output. So we broke it apart so we could make the call to the server when it came back, and then piece together the attributes later after. So we didn't have to do that in the response. So we let all the server side stuff is in this one function. And here's our load data frame kind of reworked a little bit. So this is folded. It's the same sequential. I can get you the code if you want. Here's that min workers to make sure we don't have any. I think I ran about 200 workers on this. So with the thread pool executor as a worker, I'm going to store them as a dictionary just in case something goes wrong. I can put that ID number in and see what happened to it as opposed to a list, but you could use a list, tuple, whatever. So for the unique ID and address, and here's that zip again, just because it's faster than other iterations. We're going to submit them with executor.submit to the geocode. So that's function we looked at. We're going to geocode the address and the unique ID. And we're going to add that future as the identifier, or we're going to add that future. That's dumb. I should have done it the other way. We're going to add the unique ID to this map, and then the done iterator. As those are completed, we're going to add it to this done iterator, which is going to use TQDM, which is that cute little progress bar. So it says as those are done, the total number of items that we had to process, tell us when they're done. And then as they are finished, we're going to process those results. This star notation basically just says, instead of giving a group of like a list of multiple little lists, break them up into one big list. Append that list to the output and return the results. So here, let's take a look at it. So this is our same 6,000 addresses sequentially threaded. It's a little bit quicker. So remember, we were running about 13 a second, and now we're running about 100 or so. So you can see it kind of slows up and hangs up right there on the things that are slower processes because the faster ones come back while we wait on the slower ones, but we're not stuck doing nothing as those come back. So as opposed to 10 minutes, it took 25 seconds. So for you people doing the math, that is 25 times faster or 2,500% faster. So I did not lie to you. I did not mislead you. It is quicker. Now, this is the part that I ask you if you want to go on because there is more dark magic ahead. There is, but a faster way. Yes. Oh, you guys are great. Gluttons for punishment. I love it. Let's talk about the future. Talk about the future of Python program, and that is asynchronous programming. So one problem with threaded coding is that each of those little threads does take a little bit of overhead. It takes a little bit of resources to create it. It takes a little bit of resources for it to hold on, so you are limited to the number of threads you can have. In asynchronous coding, there is no limit because you have your CPU sends all the requests all at once, and as they come back, it handles the requests. Also, with threads, you don't have any control of when the thread checks. So Python just kind of sniffs around and just checks on which thread it wants to resume. And if you're doing something critical, it could mess up because it just kind of jumps back and forth and thrashes as opposed to working smoothly at one piece. But asynchronous programming is also significantly more difficult than concurrent, I find especially. So let's go ahead and see what the asynchronous version of the geocoder looks like. So we were getting about 200 a second, iterations a second before, and now we're getting about 500. So that is 6,000 addresses in 14 seconds. So that's 4,400% faster, or 44 times faster than the original sequential code. Let's take a look at the code for that. We're going to load the data frame. So this is, remember, our original read-in function. We're going to do the blank results and the pandas read and check. The big thing that's different here is right here. So we need to do a get event loop using async IO. Go back. We're going to use an event loop, which is just going to say this is our running loop that does stuff while we wait and process other things, basically. You want to set debug to true, which will give you debugging assistance. Not much, but it will give it to you. And we're going to run the async geocoder using that data frame and our items. We specify that just to have an end point. And then we're going to run that loop until complete. You can either run the loop forever for like GUI things, or you can run it till the end of the function. Depends on which way is easier. And then we're going to close that loop. So then for the response that we get, once that asynchronous part's done, we'll process the results and append them. So here's the asynchronous magic. So the async geocoder, you use async def to specify an asynchronous function. And then we're going to use async with AIO HTTP client session as a session. It's a little different than response, but that's the function for it. So we're going to do a list comprehension here. So we're going to just say this geocode function for those address, unique ID, and session. So basically, we're just building a list of functions. So it'll be like this geocode call. It's just a list of calls. And then for those addresses in that list, we're going to send them to the async geocoder. And then as they're completed, add them to that iterator, just like we did with the other TQDM. And then for each future in that iterator, we're going to use the await function. So basically it says, hey, submit all this stuff. And as they're done, we're going to await the future to come back from the async geocode. Oh, hey, none of my questions were coming up. I apologize. I'm so sorry. They just all showed up.
Ben, just wanted to let you know we've got 10 more minutes.
Yep, we are almost done. Thank you. I like the Ferrari, Caleb. So then we're going to use async with session get geocode as a response, and it's the same geocoder, the same response. We're going to await that response from the geocode. So async works on those asyncs and awaits. When I wrote this was a couple years ago, so they kind of changed a few things, made it a little easier, but it's kind of finalized now. Same thing, get the result, kick out the return. Like I said, it's a little more difficult, but it is faster. So some food for thought, make sure you know your problem that you're trying to solve, because problems can be sped up with async geocoder or async sequential threading, etc. but only specific problems can be solved. You got to know what you're trying to make quicker. You got to know which pieces are actually slow, and also make sure you need to speed up your script. It's very tempting. Once I learned how to do this, I started threading everything, and then I kind of took a step back and it was like, well, this went from 10 seconds to process down to 7, and it took me an extra 2 hours to code it. So you might not need to do it. Also, I would say that you should write your problems sequentially first to make it easier on your brain, and then you can break it apart more to concurrent or parallel later. And with that, that's all.
Thank you, Ben.
Any questions? Buy a Threadripper. I like that. If you can find one.
We're getting a lot of thank yous.
I see that, yeah. Yeah, you could do some multi-threading on multiple cores, but once you break it apart to multiple cores, you run the risk of, because each Python interpreter is independent, so they have no communication between each other. So you run the risk of memory races. So this one will get to this one and this one will do the same thing. So you would have to break them apart into pieces up front and then send those out to each of those pools to be threaded and come back. So, and then you also have the overhead of breaking them apart, splitting them apart, and then rejoining them back into the pool. So if you had like several million, maybe. If anything less than that, probably not. Have you considered using this Python script in an ArcGIS app or any application that can be shared? I have it. It's out. If you want it, you can. We could. Richard Stevens, I will give him a shout out because he wrote the original Geocoder. I am running through the ArcGIS install of Python. Yes, I am using the Python that comes with Pro, so the 3.0 version as opposed to the 2. Yes, you can use that for the Indiana Geocoder. Interestingly, it runs one at a time too, so you might be able to get away with using Esri's service, and because it's one submittal as opposed to a batch, so they might not notice, because it might just be like you're making 1,000 calls to the website at once without using tokens. But I like the composite locator better anyway. Yeah. Okay, good. So you guys are using that, Richard? Okay, cool. I did find out too that there is this whole, as of like yesterday, this whole presentation might be worthless because you can maybe submit a batch as opposed to geocoding individual addresses. You could just submit the whole thing and it might be more efficient. But the method still works. It still applies to other things. It's just, I had no idea about that API until the other day when I looked at it. I don't have it published anywhere. I can send it to people, or I can put it out. Like Sean said earlier, I am the head of the IGIC developer support group, and we maintain a GitHub site. So I could put it out there on GitHub so everybody could get it. But just email me and I'll give you all of them, and I can talk it to you through you, and you can see the different examples. We can make the presentation available as well, although it's mostly just nonsense and pictures, so the recording's probably more valuable. So. I think Richard was, I think they said that they had plans to use it like in web apps too. I think that's what they were doing. So you can use this in other pieces of stuff as opposed to just doing it like I do it as a once-off processing thing. Another way that I use the threading is I have an image compression script, and it takes like our imagery tiles, and It takes our imagery tiles that are TIFFs and JPEG compresses them, so they go from like 500 megs a tile down to like 10. So JPEGs was invented for cameras. It's really, really good at creating loss data, but you can't visually tell the difference. So it'll compress that tile so it looks the exact same to the human eye, but it's orders of magnitude smaller. So our original TIFF file package will be like, 20 gigs or whatever, and I'll compress all those down and then build tiles on top of those compressed images. And the whole tile package down to like zoom level 23 will be smaller than the original TIFF files to host. And I use the multi-threaded version to process that, because once you make a like a command line GDAL submit call in a command line, then you're in Windows world, and your operating system's really, really good at handling lots and lots and lots of threads and parallels, and it'll handle all that. So basically, it kind of just says, Python will just kick it out to the operating system and says, I don't worry about what happened out there. So then Windows takes over. So it's kind of a neat way to sneak around the global interpreter limitations, because you're just making calls against command lines in your computer. So it's kind of a sneaky little trick, and I can make that available to anybody who wants to see that too. Any of my stuff too, it's usually written just for me, so your mileage may vary. It's got some stuff, but
Ben, this is Sean. Which geocoder are you using from the state? Is it we have a couple. We have a version 2 that was published recently.
Yeah, so when this was written the first time, it was Composite Locator, but now I've swapped them out for version 2. So
okay, and just for everybody, the version 2 is the latest locator built on the 2020 data harvest collection, and as we go forward with the collections, we'll continue to just exchange the information behind that version 2 locator. That is a WGS 84 coordinate system. That's one of the big differences between the prior version.
Yeah, and the composite locator is very nice too, because like as opposed to your Esri or Google Earth or any other locator you're going to use, they don't have a lot of address points typically. And since, like Sean said, this new one comes with the 2020, the address dots that I put in, like apartments, half addresses, things like that we locally know where they are, they're in there. So you'll get an address match as opposed to just a street level guess. So very handy. Especially since Luca happened, and everybody had to kind of go through that stuff. So I will also give a shameless plug. Come to IGIC Developer Support Group. We'd love to have you. Send me an email. I will add you to the mailing list. We meet quarterly, presentation, talk about projects we're working on, getting help from other people. And we also have a Slack workspace that you can ask questions to other developers in Indiana. You can get help, share ideas, share what you're working with. There's some people working on some Django web page projects. There's some people working on some machine learning imagery classification stuff, some SQL stuff. So free to join, sign on, send me an email. Shameless plug.
Well, thanks, Ben. This is a great presentation. Had a lot of attendance, and it looks like it's the top of the hour. So, okay. Any other last minute questions?
Great job, Ben.
Thank you.
Glad you're able to do it this year.
Yeah, me too. All right. Thanks, everybody. Thanks for coming.
Bye, everybody.